Okay. Good morning, everyone. Today we are going to we'll first finish the example we haven't finished last time. So the P series. So in this example, we study the convergence of the series in this form. One, the sum of 1/n to the p power, where n starts from 1 to infinity. And so we'll go through some cases last time. Let me quickly write them down here. The first case is that when p is less than 0, then by the test for divergence, you get this is uh, the series is divergence. From the test for divergence, because the limits of the n terms when p is less than 0 goes to infinity. And then when p is equal to 0, then the series is also divergence. Again, it's from the test for divergence because the limits as n goes to infinity is equal to 1 in the case where p is equal to 0. So the limits is not equal to 0, so that means the series is divergent. Then there's one more case. It's the case when p is equal to 0, p is greater than 0. And last time we said we considered the function f of x is equal to 1 over x to the p power, which is the function that is corresponding to this function. And we want to use the integral test for this function. So first we need to check if it's suitable for the integral test. So the function f of x is equal to 1 over x to the p power when p is greater than 0 is continuous. On 1 to infinity. And again, when you use the integral test, it doesn't have to start from 1. It can start from 2 or 3 or something, as long as it's continuous, positive, and decreasing after a certain finite number. But here for this function, it's continuous on 1 to infinity, so which is the ideal case. And then it's positive. Also on 1 to infinity. And it's decreasing on 1 to infinity. These are not hard to check because it's just 1 over x to the p power. And one of the most common, or well, when p is equal to 1, you just get a function like this, and you can easily check this is a continuous positive and decreasing function on 1 to infinity, but only the case when p is greater than 0. So we can use the integral test. So and we need to integrate this function f of x on the interval 1 to infinity. And right, here we go. And so the integral of f of x, the integral of 1 over x to the p power is equal to integral of 1 to infinity of x to the negative p dx is equal to the limits as t approaches infinity using the definition of an indefinite integral of 1 to t of x to the negative p power dx. And this guy is equal to the limits as t approaches infinity of 1 over 1 minus p times t to the 1 minus p plus 1 minus 1. This is when p is not equal to 1. you just directly apply the integral formula for a power function. And if t is equal to 1, then you get a integral of 1 over x from 1 to t. And this integral is equal to natural log of x, evaluated at 1 and t. So that's equal to the limits as t approaches infinity of natural log of t when p is equal to 1. At the other endpoints, natural log of 1 is just 0. So there's only natural log of t here. And now, right. So when p is equal to 1, the sum, the integral 1 to infinity, 1 over x to the p dx is equal to natural log of t, limits of natural log of t as t approaches infinity. And this is divergence. So the indefinite integral is divergence. And so from the integral test, this implies that the series, the harmonic series, 1 over n to the p, n to the 1, and from 1 to infinity, is divergence. So we have used different methods in the previous section to show that this harmonic series is divergence. And the integral test here just verify that the results we got earlier last week. And the other case is when p is not equal to 0, then this integral 1 over x to the p dx from 1 to infinity is equal to the limits as t approaches infinity of 1 over 1 minus p times t to the 1 minus p minus 1. And there are two subcases here. The first case is when p is greater than 1, then the power, then this term here, the power 1 minus p is less than 0. So when t goes to infinity, and infinity to a negative power, that's 0. So it's just like 1 over t to the 1 p minus 1. So t to the 1 minus p is equal to 1 over t to the p minus 1. And if p is greater than 1, then this term is greater than 0. When t goes to infinity, this guy just vanish. So the limits is equal to, so in this case here, the indefinite integral is equal to 1 over 1 minus p times 0 minus 1 is equal to 1 over p minus 1. So it's divergence. It's convergence. This integral is convergence. So from the test for divergence, from the integral test, the series, the corresponding series, sum of 1 over m to the p power, n starts from 1 to infinity, is convergence. When p is greater than 1. And the other subcases is this case when p is less than 1. Then you have, in this case, you have 1 minus p is greater than 0. So t to the 1 minus p. Now you have a infinity to a positive power. and this guy goes to infinity as t approaches infinity. So so now for this case, the integral 1 to infinity of 1 over x to the p power dx is divergence. So will the corresponding series 1 over n to the p is divergence when p is less than 1 to infinity. To sum up here, right, this is the end of this example. So to sum up here, we will just write this example as a theorem. The power, the p series, this series, and 1 over n to the p, n starts from 1 to infinity. This is convergence when p is greater than 1, and is divergence otherwise. So the only case when the p series is convergence is that p is greater than 1. The other 3 cases, we'll put them together as otherwise. They are all divergence. P series is a very common series, and we will use it in the future. I think we'll use it more frequently in the future for the comparison test. Any questions about this example? Okay, let's move on. Right. The second topic in this section is testing by comparing, or the comparison test. So the comparison test is to determine the convergence and divergence of a series from another series. Suppose we have 2 series. One is AN and the other one is BN. And both series are positive series, which means all the terms in the series are positive. And the condition positive is important for the comparison test. And right, there are two cases for the comparison test. If the series Bn is convergent and An is less than or equal to Bn for all n, right, for all n, let's see, yeah, for all n, let's assume n starts from 1 to infinity here. So if this series is convergence for, if the series Bn is convergent and every term in the series An is less than the corresponding terms in the series Bn, then the Bn, the series An from 1 to infinity, is also convergent. On the other hand, if the series Bn is divergent, and right, yeah. Now this time is an is greater than the corresponding term in Bn for all n, then the series n from 1 to infinity is divergent. So it's kind of like the integral test, except here, the f of x, or the indefinite integral of f of x in the integral test is replaced by another series, Bn. And then basically you just need to compare compare An and Bn and determine whether Bn is convergence or divergence. And usually we want Bn is a series that is easy to determine whether it's convergence or divergence. For example, the P series is usually used in the comparison test. And the comparison test, you can, for example, let me give you a geometric interpretation. So the comparison test, let's just do case A. So again, suppose we have a bunch of, so we have a bunch of B. Well, we have a bunch of points which represents the terms in the series Bn, B3, then so on. And then as what we have done in the integral test, the sum of series can be interpreted as the sum of the areas of some small rectangles. So you have a bunch of rectangles because the width between the width of these rectangles are just 1. The heights are just B1, B2, B3. So the series Bn is the sum of the areas of all the rectangles. Or black rectangles. And the comparison test, the first case in the comparison test actually tells you that if you have another series, An, which means an An, each term in the An is less than or equal to the corresponding term in Bn, then, so let's say this is A1. Now A1 is less than or equal to B1. It's less than, in this case, strictly less than. And you have A2, you have A3. Then the sum of An is the sum of the series An is equal to the sum of the areas of all the red rectangles. And the first case in comparison test just tells you that if the sum of all the black rectangles is convergence or is a finite number, so will the sum of the red rectangles. So the series An. And the divergent part for the divergent counterparts of the comparison test, you can give a similar interpretation. And there's a notes for the comparison test. Just one more. So in the comparison test, we require for all n, and this this condition here can be relaxed to for all n greater than a positive number n is a positive integer. So it's kind of like the relaxation for the integral test where we don't start from 1, we start from a number that's greater than 1, and that's also valid. As long as they are all positive and it satisfies one of the condition or one of the condition in the comparison test, you can use the comparison test. Any questions, comments? Okay, let's see an example. So let's try to determine whether this series, the sum of n from 1 to infinity of phi divided by 2n squared plus 4n plus 3 converges or diverges. So for this series, we can use the comparison test. So apparently, this is the series an in the comparison test. And in order to use the comparison test, we need to first figure out what series we want to compare this series to. So right. So all right. Yeah. So for each term in this series, phi divided by 2n squared plus 4n plus 3. This guy is less than 5 divided by 2n squared. So because this one is always positive, this part is always positive, and so the denominator of the left-hand side is greater than the denominator on the right-hand side, and they have the same numerator. So this is true. This inequality is true. And first we notice. And in the meantime, the series 5 divided by 2n squared, n from 1 to infinity, this is equal to the sum of the series n from 1 to infinity of phi halves times 1 over n squared. I just factored that phi halves. Then this is equal to phi halves times the series n from 1 to infinity of 1 over n squared. So this series, the sum of 1 over n squared, this is convergence. Because this is the case when this is the case in the P series when P is equal to 2. P series. Just this part. P series with P equals 2. and p equals to p equals 2 is greater than 1, so it's convergence. So will the scalar multiple of the series. So now you have a series that's less than that. You have a series that each term of this new series, this is our Bn, this is our An. So each term in Bn is greater than the corresponding term in An. And in the meantime, the series Bn is convergent. So from the comparison test, the series 5 over 2n squared plus 4n plus 3n from 1 to infinity converges. Right. Any questions? So let's see another example. Now this time, let's see the other half of the comparison test. Now this time we want to learn about or study the convergence of this series, natural log of n divided by n, and from 1 to infinity. And right, so for this series, we have shown that this series is convergent. Well, it's divergent using the integral test last time. So this is divergence by the integral test last time. Today we are going to use a different method to show its divergence. This is divergence from test. Today we are just going to use the comparison test to show it is divergence. So right, by some calculation. So you can check this yourself. Natural log of n will be greater than 1 when n is greater than 3, well, greater than or equal to. Greater than or equal to. And this is easy to check because the boundary when natural log of n is equal to 1, you get n is equal to e. Natural log of e is equal to 1 because e is the base of the function of the natural log. So for any number that's greater than e, you always have a natural log of that number is greater than 1. And because 3 is greater than e, so natural log of n is greater than 1 when n is greater than or equal to 3. And I add equal here because we only consider the positive integers in the series. And then from this results here, we have natural log of n divided by n is greater than 1 over n when n is greater than or equal to 3. So this matches the notes I put earlier. So n doesn't, you don't have to have every term in the series that's greater than the corresponding term in the other series. In the series you compare it to, you can, the n can start from a finite number and continue all the way to the infinity. It doesn't have to start from the beginning. And the comparison test is still valid for this case. And then in this example, since we have natural log of n is divided by n is greater than 1 over n when n is greater than 3. So, and right, this is part 1 of the comparison test. And we can call this this guy an and this guy bn, because this series is the series we want to compare it to, compare the original series to. And on the other hand, we know the series 1 over n. This is divergence because it's the harmonic series. Or you can say it's the p series with p equals 1. And so it's divergence. We have shown its divergence before. And right. And now you have series an. So now from the comparison test, from part B of the comparison test, first. Your original series, natural log of n divided, every term in the original series, natural log of n divided by n is greater than a term in a divergent series, 1 over n. So from the comparison test, this series, natural log of n divided by n is divergence.
I have a question.
Sure.
So when we're doing like homework and like the test, is it okay to just put that like due to the harmonic series or p series, or do you want us to show the work?
You can just say it's a p series with p is equal to something.
Okay,
then,
thank you.
Yeah, the p series, the results for the p series is stated as a theorem, so you can just use it directly. You don't have to show that the p series is convergence or divergence again in the future if you want to use the p series.
Okay, thanks.
Yeah. Any other questions? So I will talk about how to choose a series that you want to compare. How to choose a series that, or how to choose the series Bn next time after we finish the next test. So there is a variance for the comparison test. It's called the limits comparison test. So again, we suppose we have two series. Suppose that the series An and Bn are a series with positive terms. And if the limits of the ratio of each term in the series An and Bn, so it's the limits of An divided by Bn is equal to a constant C. And the C is a finite number, so it's not infinity or negative infinity. And C is a positive number. C is greater than 0. then we will have either both of them convergence, either both of them are convergence, or both of them divergence. Both of them are divergent. And because we require the series of positive here, so this so the restriction for C here is actually C is just a finite number. It's a non-zero finite number. It's not equal to infinity, and C is not equal to 0. And then as long as the limits exist, then it's equal to and C satisfied these two conditions, then the two series either converges together or diverges together. And we can just directly use, we can just revisit one of our example today. 3. So in example 1, we have used the we have used the comparison test to determine the convergence and to determine that this series is convergent. Now, if we want to use the limits comparison test, we will still compare this series to the series plus 3 to this series, sum of phi halves, or let me put the phi halves in the sum 5 divided by 2n squared. We'll still compare this series to the series phi divided by 2n squared, but this time we will not use the comparison test. We will instead use the limits comparison test. Using the limits comparison test, or for future use, I would just call this LCT, the abbreviation of the limits comparison test. Then, right, in order to use the limits comparison test, we need to calculate the limits of the ratio. So in this case here, this is the original series, which is labeled as AN. This is the new the series you want to compare the original series to. So this is our BN. And the limits of the ratio AN divided by BN, n goes to infinity. This is equal to the, well, AN is 5 divided by 2n squared. Put the limits first. Limits as n approaches infinity of 5 divided by 2n squared plus 4n plus 3. The bottom is 5 divided by 2n squared. And this is equal to the limits as n approaches infinity. You can do some algebra here. You can cancel this term. You get 1 divided by this over 1 divided by 2n squared. And then just some algebra, you get 2n squared on the top and 2n squared plus 4n plus 3 on the bottom. And we have seen this this kind of limits before. And for this, you can either just use the L'Hopital's rule. You replace all the n with x. Then you just calculate. So you can use the L'Hopital's rule. this is method 1. You can use the L'Hopital's rule to calculate the limits as x approaches infinity to x squared divided by 2x squared plus 4x plus 3, which is not necessarily exist, but in this example it exists. So this method actually works fine. And use the L'Hopital's rule, you calculate the derivative of the top, which gives you 4x divided by 4x plus 4x approaches infinity. And then you use the L'Hopital's rule again, get the limits as x approaches infinity of 4 divided by 4 is equal to 1. So this is one way to do it. Another way is that you just divided the numerator and the denominator by the highest power term in the numerator and the denominator. 3. And for this example here, the highest power term is the n squared, or you can use the 2n squared. It doesn't really matter here. Then you get 2n squared divided by n squared, 2n squared divided by n squared, plus 4n divided by n squared, plus 3 divided by n squared. And then you will realize when you simplify these terms, you will realize this term, this term goes to 0, this term goes to 0. So what's left is just 2 divided by 2, so it's equal to 1. Either way is fine here to determine in order to determine the limits of this function or the sequence. And then no matter which way you choose, you will get the limits of this guy is equal to 1. This is neither 0 or infinity. So we can use the limits comparison test. Right. So by the limits comparison test, LCT, the series AN by the limits comparison test, as well as the fact that this series 5 divided by 2n squared is convergence. We have this series, the original series 2n squared plus 4n plus 3 is also convergence. Any questions? So you may wonder, why do we have this limits comparison test? Why we already have a comparison test. For this example, we can also use the comparison test to solve it. Then why would we introduce? Why do we want a limits comparison test? It's because the restriction in the comparison test is the condition in the comparison test is too restrictive, and it can fail. For example, like this. So now suppose we want to determine the convergence and divergence of this series, 5 divided by 2n squared minus 1. And if you want to use the comparison test, for example, if you want to use the comparison test and compare it to the series 5 divided by 2n squared, if we compare it, use the comparison test. And compare it to, well, a reasonable choice here is just 5 divided by 2n squared. And if we want if we compare this series to this series, then you will have, what you will get is that Bn is equal to 5 divided by 2n squared, the new series, the series you want to compare to, is greater than an. Well, sorry, this time it's less than 5 divided by 2n squared minus 1 is equal to an. Because this guy has a larger denominator. And now what you will see is that you have a series an is greater than bn, but unfortunately bn is convergent. And this is not the case. This doesn't match either of the case. Well, this doesn't match any of the case, or neither of the cases in the comparison test. Because in comparison test, if we have an is greater than bn, then we want bn as divergence. But unfortunately here, the bn is convergence. So this doesn't match. Either case, either conditions in the comparison test. Because we have a series, we have the original series is greater than the series we are comparing to, and the series is convergence, not divergence. But if we use the limits comparison test here, and still compare this series to, we still compare the series, the original series to this series, 5 divided by 2n squared, then the limits of the ratio as n approaches infinity is equal to the limits as n approaches infinity of 5 divided by 2n squared minus 1 divided by 5 divided by 2n squared. Then this is equal to the limits as n approaches infinity of 2n squared divided by 2n squared minus 1. And again, for this limits, you can use L'Hopital's rule or just divide both the numerator and denominator by the highest power term in the fraction. Then you get this is equal to 1. And this is not, and 1 is it's neither 0 nor infinity. So it satisfied the condition in the limits comparison test. The ratio, and then since this series 5 divided by 2n squared is convergent from the limits comparison test from LCT, this series 5 divided by 2n squared minus 1 is also convergent. Any questions or comments? Okay, we'll meet tomorrow.